let me first of all introduce a little bit more of notation, something called summation notation. So if I have numbers, A1, A2, A3, then I can write the sum A1 plus A2 plus A3. A shorthand for that is this notation, K, an index variable going from 1 up to 3 with a subscript. These two things mean exactly the same thing. That way, if we're doing 100 subintervals, the idea is that we don't want to have to write out a sum with 100 terms. We'll just have a sum with a formula in it with K going from 1 through 100. Similar to what we just did in the program, where we had to come up with a formula for those areas that depended on that index variable K that was going from 1 up to whatever we told it to go up to. Properties of summations. If we take the sum of one list of numbers AI plus another list of numbers B sub I from 1, or K, I tend to use I, but the book uses K. Well, what this means is A1 plus B1 plus A2 plus B2 plus A3 plus B3. That's a list of 6 numbers. That list of 6 numbers can be written in a different order. I can add all the A's, and then I can add all the B's, which would be the sum K going from 1 up to 3 of A sub K plus the sum K going from 1 up to 3 B sub K. There's a place where this shows up in the book, just to kind of reference the relevant thing. It's a table down in the middle of page 308. So all this formula says is that addition is commutative. I can add up a list of numbers by, or 2 lists of numbers by adding them term by term and combining the results here, this first thing. Or I can add up all the A's, add up all the B's, and take the sum of that. If I have C a constant, then K equals 1 to 3. If I take each one of the A's and multiply it by this constant, that's the same thing as C times A1 plus C times A2 plus C times A3. That's C times the sum A1 plus A2 plus A3, which is C times the sum K going from 1 up to 3, A sub K. And again, that index should be K, not I. In other words, all that this formula, which is the third formula in that table, says is the distributive property of multiplication over addition. It's just elementary school arithmetic written in a really complicated looking form. If I take K going from 1 up to 3 and put a number in there like 5, that just means when K is equal to 1, we write down a 5, plus when K is equal to 2, we write down a 5, when K is equal to 3, we write down a 5. This is just 3 times 5. And that's the constant value rule. That's rule number 4. That if I add a constant to itself n times, I just get n times a constant, which is actually the first definition you saw for multiplication back in about 3rd grade. Multiplication was repeated addition. There's a legend about the mathematician Gauss that his teacher, once upon a time, decided to keep the class busy in elementary school by giving them this list of numbers to add up. And before the teacher had even finished with writing the last 0, Gauss had the answer and wrote it on his little chalkboard and took it up to the teacher. So are you as fast as Gauss? How would you add up that list of numbers from 1 up to 100? Take the what? Okay, so what's the mean? Okay, the halfway value 50. Yeah, that's somewhere along the line of what Gauss actually did. If you take the observation that they go in pairs, that if you group them, the first one and the last one add up to 101. These two add up to 101. The next pair adds up to 101. The middle pair is going to be 50 plus 51. And so I get a first pair, a second pair. This one was 1 plus 100. This was 2 plus 99. So how many pairs? That's being counted by this first number. So there are a total of 50 copies of 101. That allows us, that idea, if you generalize it, says if we add up from 1 to n, the number's k, in other words, 1 plus 2 up to n. Yes, so this is actually 100 times 101 over 2. The 50 is there for a reason, right? It actually is, so it's your value of n, how many terms you're adding up, times 1 more, because the pairing gives you the 1 more. So that's n times n plus 1 over 2. Now k goes from 1 up to n, that's just the shorthand that says add up 1 plus 2 plus 3 up to n. And we get this formula for adding up consecutive integers. Similar formulas, but what are harder to prove, are that if you add up the sum of the first k squares, you get n times n plus 1 times 2n plus 1 over 6. Try it out with a few small numbers. Add up the first 10 perfect squares by hand and verify that you get 10 times 11 times 21 all divided by 6. And then there's another one that's kind of surprising. This is going from 1 up to n. The sum of the first n cubes, 1 cubed plus 2 cubed, so 1 plus 8 plus 27 plus 64 and so on, is n times n plus 1 over 2, the whole thing squared. It's just the square of what you got when you added up the first n integers.